Hello everyone, hope you are all doing well. Welcome back to our channel, your unique gateway to knowledge and understanding. If you haven't yet liked, subscribed, or shared, make sure you do, because this channel is completely different from the rest. Here, we bring you stories that expand your mind, enhance your knowledge, and allow you to explore the universe in ways you have never imagined. From the tiniest particles of matter to the vast galaxies stretching across the cosmos, from the origin of life to the rise of humanity, this channel is dedicated to presenting detailed, immersive, and enlightening narratives. Today, we take you on an extraordinary journey, a story that begins before time itself, in the depths of the quantum void, and travels all the way to the creation of the modern world. This is a story of the universe, of stars and galaxies, of Earth and life, and finally, of humans who built civilizations capable of looking back and understanding their cosmic origins. In the beginning, there was nothing, or rather, there existed a quantum void, a state beyond space, beyond time, beyond comprehension. In this void, energy flickered in and out of existence, in a dance dictated by the mysterious laws of quantum mechanics. Tiny fluctuations occurred spontaneously, creating ephemeral particles that appeared and vanished in an instant. This void, though seemingly empty, held infinite potential, containing the seeds of everything that would come into being. It was here, in this silent, invisible stage, that the universe waited to emerge. Then came the first moment, an event so profound that it marked the birth of time itself. In a singularity smaller than an atom, the universe expanded in a sudden burst known as the Big Bang. Space stretched outward, energy surged, and the fundamental laws of physics crystallized. In that instant, cause and effect began, and the universe became a dynamic, evolving entity. Photons raced across space, subatomic particles collided and combined, and the stage was set for the formation of matter, energy, and eventually life. Time, which had no meaning before, began its relentless march forward. Within the first 3 minutes, the universe was an unimaginably hot, dense fireball. Quarks combined to form protons and neutrons, while electrons roamed freely. Nuclear fusion in these primordial conditions formed the first hydrogen and helium atoms. Tiny density fluctuations in this early universe acted as the blueprint for future cosmic structures. These first 3 minutes established the fundamental ratios of matter, laying the groundwork for stars, galaxies, and planets. The universe had set the stage for everything that was yet to come. Over millions of years, gravity began its slow but inexorable work. Clouds of hydrogen and helium, denser than their surroundings, began to collapse under their own weight. Within these clouds, the universe's first stars were born. These stars were not like the ones we see in the night sky today. They were colossal giants, hundreds of times the mass of the sun, burning with extraordinary intensity. Within their core, nuclear fusion forged heavier elements: carbon, oxygen, nitrogen, and iron. When these massive stars ended their lives in supernova explosions, they scattered these elements across space, seeding the cosmos for future stars, planets, and eventually life itself. The ignition of the first stars ended the cosmic dark ages, bathing the universe in light for the very first time. As these stars clustered, the gravitational forces that bound them began shaping galaxies, vast islands of stars, gas, and dust, held together by dark matter. Spirals, ellipticals, and irregular galaxies emerged through rotation, collisions, and mergers. These galaxies were not merely collections of stars. They were complex ecosystems, recycling material through generations of stellar birth and death. The universe, once a featureless expanse, now displayed structure, organization, and the promise of complexity. Within one such galaxy, a dense molecular cloud began collapsing under gravity, giving rise to our Sun. As the core of this cloud compressed, it heated up to millions of degrees, igniting nuclear fusion. The Sun blazed into life, providing energy, heat, and gravitational order to the surrounding protoplanetary disk. Within this disk, dust and gas coalesced into planetesimals, which collided and accreted to form the planets. Our Earth, the third planet from the Sun, began its journey as a molten, violent world, constantly reshaped by impacts, volcanism, and the formation of its magnetic core. One of the most dramatic events in Earth's early history was the collision with a Mars-sized body, known as Theia, which created the Moon. This impact stabilized the planet's axial tilt, giving rise to relatively stable seasons and tidal systems, which would prove essential for the development of life. Outgassing from volcanoes formed a primordial atmosphere, while condensation of water vapor created oceans, the cradles of life. Plate tectonics, volcanic activity, and chemical cycles gradually established a stable, habitable environment, enriched with elements forged in the cores of ancient stars. Within these oceans, life emerged. Simple molecules combined to form RNA, proteins, and lipids, giving rise to the first protocells. These early cells were capable of self-replication, metabolism, and gradual adaptation. Over millions of years, life diversified, producing oxygen through photosynthesis, shaping the atmosphere, and paving the way for multicellular organisms. The first breath of life was the beginning of a process that would continue uninterrupted for billions of years, leading to all complex life forms. From this evolutionary tapestry, humans emerged. The first members of the genus Homo evolved in Africa, developing tools, fire, and social structures. Anatomically modern humans, Homo sapiens, appeared around 300,000 years ago. They were intelligent, adaptable, and inventive. They migrated across continents, creating communities, language, and culture. Through agriculture, humans shifted from nomadic lifestyles to settled societies, developing villages, cities, and eventually civilizations. Writing, governance, trade, and art flourished, reflecting human ingenuity and ambition. The rise of the modern world is the culmination of this journey. Human curiosity, exploration, and technology transformed the planet. Societies developed science, philosophy, and global networks. The Industrial Revolution accelerated human impact, connecting civilizations, mechanizing production, and harnessing energy on an unprecedented scale. Today, humanity stands as a planetary architect capable of altering ecosystems, exploring space, and comprehending its cosmic origins. From the quantum void to the first stars, from galaxies to our Sun and Earth, from the first cell to intelligent humans, this story is the narrative of existence itself. Every atom, every star, every organism, and every human is part of a continuous chain linking the present to the very beginning of time. This is the journey of the universe, a journey that continues with each discovery, each exploration, and each step toward understanding the cosmos. If you enjoyed this story, make sure to like, subscribe, and share. Support our channel to continue receiving detailed, educational, and immersive journeys through the mysteries of life, the universe, and human history. Stay tuned for more stories that expand your mind, enrich your knowledge, and connect you to the cosmos.
The story of our universe begins in a realm beyond comprehension, a vast emptiness known to scientists as the quantum void. This was not emptiness in the ordinary sense. It was a seething, invisible field of energy, where the very laws of physics as we understand them were suspended. Imagine a place with no matter, no light, no time, and no space as we experience it, yet paradoxically, this void was alive with potential. Particles and antiparticles flickered in and out of existence in the blink of an eye, appearing spontaneously before vanishing again, governed by the strange and mysterious rules of quantum mechanics. Physicists suggest that this void was not a static emptiness, but a dynamic, restless state filled with fluctuations and virtual particles. It is within these fluctuations that the seeds of everything to come were sown. The void was governed by the uncertainty principle, where nothing had a fixed position or momentum, and yet the possibility of creation was everywhere. In this paradoxical landscape, energy could manifest as matter, giving birth to the first sparks that would eventually lead to stars, galaxies, and planets. The quantum void challenges human intuition. We try to picture it as an empty space, but in reality, it was a cosmic canvas of probability, a stage set for the grand drama of existence. The questions of why this void existed, or why it held such potential, remain among the deepest mysteries of science. Philosophers and physicists alike speculate whether it was a spontaneous emergence, a fluctuation in a larger multiverse, or perhaps a design embedded within the very fabric of reality. Yet even in its silent stillness, the quantum void carried the echoes of all that was to come. Time had not yet begun, yet possibilities stretched infinitely. In this fertile emptiness, everything that would ever exist lay dormant, waiting for the moment when the universe would awaken. The void, in essence, was both the womb and the seed, a paradoxical beginning where nothing and everything coexisted. From this enigmatic state emerged the first tremors that would ripple across existence, leading inevitably to the birth of time itself, the next chapter in the universe's unfolding saga. Before the universe had a name, before the first particles danced in the void, time itself did not exist. In the quantum void, there was only potential, a timeless expanse where past, present, and future were meaningless. Yet from this delicate balance, the very fabric of reality was poised for transformation. The first moment, often referred to as the beginning of time, was the instant when the universe leapt from potential into existence. Physicists describe this event as the cosmic singularity, an incomprehensibly small, dense point where all matter, energy, space, and time were compressed. In that infinitesimal instant, the laws of physics as we know them, gravity, electromagnetism, nuclear forces, were born along with time itself. Imagine a clock that had never existed suddenly starting its first tick. This was the beginning of chronology, cause and effect. With the inception of time came movement, expansion, and transformation. The universe did not expand into empty space. Rather, space itself began to stretch, creating dimensions and setting the stage for the first particles to emerge. Time allowed change and evolution to occur. Without it, energy could not transform, particles could not collide, and the universe could never have progressed beyond its initial potential. In this first moment, the universe was an unimaginable fireball of energy, smaller than an atom, hotter than a billion suns, and vibrating with the intensity of creation itself. From this singular event, causality cascaded forward. The first quarks formed, photons began their journey, and the foundations of matter were set. The birth of time was not a gradual process. It was a sudden awakening, a cosmic heartbeat that initiated the rhythm of everything that would follow. Philosophers and cosmologists alike ponder the paradox. If time began with the universe, What does before mean? Perhaps there was no before, only the endless, ageless void, until that first moment ignited existence itself. It was this instant that transformed the quantum void from potential into a universe in motion, setting in place the laws and structures that would eventually lead to stars, planets, and life. The first 3 minutes, birth of matter as the universe surged into existence. The first 3 minutes became a cosmic crucible, where energy transformed into matter, and the foundations of all we know were forged. This period, brief by human standards but monumental in cosmic terms, witnessed the universe cooling from its initial inferno, allowing the first particles to emerge. During these fleeting minutes, the searing energy of the newborn universe began to condense into fundamental particles. Quarks combined to form protons and neutrons, the building blocks of atomic nuclei. Electrons, the lightest of charged particles, roamed freely, their paths guided by the nascent electromagnetic force. The universe, though chaotic and dense, was governed by physical laws that had crystallized in the first moment, dictating the behavior of these particles and laying the groundwork for the first atoms. Within the first 3 minutes, nuclear fusion began, an extraordinary process where protons and neutrons collided to form the simplest elements, hydrogen and helium. These tiny nuclei carried immense energy, glowing in the searing plasma that filled the cosmos. Though the universe was still opaque, a radiant heat pervaded every corner, a silent testimony to the birth of matter. The first matter was not yet organized into stars or planets. It was a diffuse, primordial soup, yet pregnant with possibility. Minute fluctuations in density, seated in the quantum void and magnified by expansion, created the patterns that would later shape galaxies and clusters of stars. In this early chaos, the seeds of structure were planted, invisible threads weaving the future architecture of the cosmos. These 3 minutes also determined the cosmic balance. The ratio of hydrogen to helium, the slight excess of matter over antimatter, and the distribution of particles were all fixed in this short window. Had these conditions been even slightly different, the universe might never have formed stars, planets, or life. The first 3 minutes were, in essence, the universe's blueprint, written in the language of particles and energy. By the end of this brief epoch, the universe had grown unimaginably larger, cooled enough to allow further organization, and transformed from pure energy into the matter that would eventually coalesce into galaxies, stars, and planets. These minutes marked the universe's first steps toward the complexity we witness today, a delicate dance between chaos and order that would unfold over billions of years. After the first matter had formed, the universe entered a cosmic twilight, a period often called the Dark Ages. Hydrogen and helium, the first elements, drifted through space as a cold, invisible fog, with no stars to illuminate the void. Yet, hidden within this darkness were tiny regions slightly denser than their surroundings, the seeds of the first stars. Gravity, the subtle sculptor of the cosmos, began its patient work, pulling matter together over millions of years. As these clouds of hydrogen and helium contracted, they heated up at their cores. When the central temperature reached millions of degrees, nuclear fusion ignited, and the very first stars blazed to life. These were not the modest stars we see today. They were colossal giants, hundreds of times more massive than our sun, burning with an intensity that dwarfed entire galaxies of modern stars. Their lifespans were brief but brilliant, lighting the darkness and marking the universe's transition from a cold, empty expanse to a realm of radiant energy. The ignition of the first stars did more than illuminate space. It altered the universe fundamentally. Fusion within these stellar furnaces created heavier elements such as carbon, oxygen, and nitrogen, which were scattered into the cosmos when these massive stars ended their lives in supernova. These elements, essential for planets and life, were forged in the heart of stars, turning the universe into a cosmic chemical factory. Moreover, the light from these stars ended the Dark Ages, allowing photons to travel freely, a phenomenon known as cosmic reionization. The universe was no longer shrouded in darkness. It began to glow with the first starlight, revealing patterns, structures, and the beginnings of the galaxies that would dominate the heavens. The birth of the first stars was a moment of awakening. From the invisible threads of matter and the gentle pull of gravity emerged brilliant furnaces that not only shone, but also set the stage for all subsequent cosmic evolution. Without these early stars, planets could not form, life could not arise, and the universe would remain a silent, dark void. With the first stars blazing in the cosmos, matter began to organize on an even grander scale. These stars were not scattered randomly. They clumped together under the invisible hand of gravity, forming the earliest stellar communities. Over millions of years, these clusters grew denser, pulling in more gas, dust, and stars, gradually shaping the colossal, swirling structures we now call galaxies. Galaxies are the universe's architectural marvels, vast islands of stars, gas, and dark matter bound together in cosmic harmony. Dark matter, an invisible yet dominant form of mass, played a crucial role. It acted as a scaffold, guiding the ordinary matter into filaments, sheets, and clusters. Within these regions, gravity pulled hydrogen and helium into spiraling clouds, forming stars and galactic cores where stellar density was highest. The shapes of galaxy spirals, ellipticals, and irregulars emerged from a combination of rotational dynamics, collisions, and mergers. Young galaxies often collided violently, triggering bursts of star formation and scattering heavy elements throughout space. Each collision and interaction was a step in a cosmic dance, gradually building larger, more complex galaxies. The formation of galaxies also set the stage for the universe's chemical enrichment. Supernova explosions from massive early stars seeded the interstellar medium with heavier elements like carbon, oxygen, and iron. These elements, forged in stellar cores, became the raw materials for future stars, planets, and ultimately, life itself. Galaxies were not merely collections of stars. They were cosmic engines, continually recycling matter and energy, shaping the structure and destiny of the universe. By the time the universe was a few billion years old, galaxies had formed in a spectacular variety, from elegant spirals like the Milky Way to massive ellipticals, each containing billions of stars. The cosmos had transformed from a uniform sea of gas into a tapestry of luminous islands, interconnected by vast cosmic filaments, glowing with the first light of countless suns. The formation of galaxies marked a turning point. The universe was no longer a scattered collection of stars, but an organized, dynamic, and evolving system. Within these galaxies, future stars, planets, and life would find their place, and the stage was set for our Sun and Earth to emerge billions of years later. How the Sun was born billions of years after the first galaxies had taken shape. A quiet region within one such spiral galaxy, the Milky Way, harbored a dense cloud of gas and dust known as a molecular cloud. For millions of years, this cloud drifted through space, cold and silent, until a disturbance, perhaps the shockwave from a nearby supernova triggered gravitational collapse. Within this collapse, the first seeds of our Sun began to take form. As gravity pulled the gas and dust inward, the cloud condensed into a dense core, increasing pressure and temperature at its center. This core, a protostar, radiated heat as atoms collided and compressed. Over time, the temperature in the core rose to millions of degrees, enough to ignite nuclear fusion, the process that converts hydrogen into helium and releases enormous amounts of energy. In that moment, the Sun was born, a brilliant new star illuminating its surrounding region. The Sun's birth also created a protoplanetary disk, a swirling plain of leftover gas and dust encircling the young star. Within this disk, matter began to coalesce into planetesimals, the building blocks of planets, moons, asteroids, and comets. Our solar system was forming in a delicate, yet violent process of collisions and accretion, sculpted by gravity and shaped by the young sun's radiation. The sun's energy was more than a source of light and warmth. It became the central engine of our solar system, governing the orbits of planets and providing the conditions for life to eventually flourish on Earth. Its stability and nuclear longevity, lasting billions of years, would allow the evolution of complex ecosystems on one small planet within its orbit. The birth of the sun was a turning point in cosmic history. From the chaotic, diffuse clouds of interstellar gas emerged a star capable of sustaining a solar system. Its formation illustrates the universe's remarkable ability to transform simple elements, born in the first stars, into structured, life-supporting systems, paving the way for the planets and eventually humans to exist. Long after the sun had ignited, the swirling protoplanetary disk surrounding it became a cosmic workshop where the building blocks of planets were forged. Within this disk, microscopic dust grains collided and stuck together, gradually forming larger clumps called planetesimals. These collisions, over millions of years, produced increasingly massive bodies through a process known as accretion. Among these, one particular body, forming in the orbit we now call the third from the sun, began to grow, eventually becoming Earth. The early Earth was a turbulent, hostile world. Its surface was bombarded by countless asteroids and comets, delivering both catastrophic impacts and essential ingredients for life. These collisions generated enormous heat, melting portions of the young planet and creating a magma ocean. Gravity ensured that denser materials, such as iron and nickel, sank to the center to form the core, while lighter silicates floated upward to form the mantle and crust. This differentiation laid the foundation for Earth's magnetic field, generated by the spinning, molten iron core, which would later shield the planet from deadly cosmic radiation. Around 4.5 billion years ago, a giant impact event reshaped Earth forever. A Mars-sized protoplanet, often called Theia, collided with the young planet. The tremendous force ejected vast amounts of material into orbit, which eventually coalesced to form the Moon. This monumental event not only stabilized Earth's axial tilt, giving rise to relatively stable seasons, but also contributed to tidal forces crucial for the future development of oceans and life. As Earth cooled, volcanic activity and outgassing released water vapor, carbon dioxide, and other gases, forming a primordial atmosphere. Water vapor condensed to create the first oceans, covering a significant portion of the planet's surface. These oceans became a cradle for the chemical reactions that would eventually lead to life. The atmosphere, initially hostile and devoid of oxygen, slowly evolved through complex geochemical processes and, later, biological activity, creating a balance suitable for living organisms. Earth's surface continued to change over hundreds of millions of years. Plate tectonics emerged, forming continents and ocean basins, recycling materials, and driving the carbon cycle, which stabilized the climate. Volcanic eruptions, earthquakes, and mountain building sculpted a dynamic, ever-changing landscape. The combination of liquid water, moderate temperatures, and a protective magnetic field established Earth's habitability. It was now a world where life could take hold, a unique oasis in the cold expanse of the solar system. In addition to physical conditions, Earth's chemical composition was crucial. Elements forged in earlier generations of stars' carbon, oxygen, nitrogen, phosphorus, and iron were incorporated into the planet. These essential building blocks of life were delivered by both the early accretion process and by later impacts from comets and asteroids, which seeded the young oceans with organic molecules. The formation of Earth was therefore not a singular event, but a sequence of cosmic processes, each shaping the planet into a habitable world. From the chaotic collisions of the protoplanetary disk, to the moon-forming impact, to the gradual cooling and emergence of oceans, Earth's early history was a testament to the universe's ability to turn raw matter into a nurturing home. By the end of this epoch, Approximately 4 billion years ago, the stage was set for the first whispers of life, the initial stirrings of a process that would eventually lead to every creature, plant, and human being that would inhabit this world.
Approximately 4 billion years ago, Earth was no longer just a molten, turbulent planet. It had cooled enough to sustain liquid water, a crucial ingredient for life. The oceans, vast and still forming, acted as a chemical crucible where countless molecules collided and combined, guided by the principles of chemistry and the natural laws that had governed the universe since its first moment. It was here, within these primeval seas, that the first spark of life began. Life did not arrive fully formed. It began at a molecular level, with organic compounds interacting in a complex, chaotic environment. Amino acids, nucleotides, and lipids building blocks of proteins, DNA, and cell membranes were synthesized both through chemical reactions in the oceans and delivered by comets and meteorites. The famous Miller-Urey experiment, recreated by modern scientists, demonstrated that under conditions similar to early Earth, simple molecules could spontaneously form these essential compounds, hinting at how life might have originated naturally from inanimate matter. These molecules gradually assembled into self-replicating systems, a critical step toward cellular life. RNA, a molecule capable of both storing information and catalyzing reactions, is widely believed to have played a central role in this process. In what scientists call the RNA world hypothesis, RNA chains, floating in the nutrient-rich oceans, could replicate, mutate, and evolve, gradually increasing in complexity. This was not yet life as we recognize it, but it was the first biological system capable of continuity. The final leap from molecules to the first true cell, a protocell, required the formation of a boundary, a membrane that could separate internal chemistry from the external environment. Lipid molecules naturally formed vesicles, tiny bubble-like structures that could encapsulate RNA and proteins. Within these protocells, chemical reactions became more efficient, protected from the surrounding environment. These early cells could absorb nutrients, harness energy, and reproduce, albeit imperfectly, but they marked the transition from chemistry to biology, the moment the first life truly breathed on Earth. Once the first cell existed, evolution began in earnest. Through natural selection, these simple organisms adapted to their surroundings, exploiting energy sources such as sunlight, chemicals in hydrothermal vents, and minerals dissolved in the oceans. Some developed the ability to photosynthesize, slowly releasing oxygen into the atmosphere, setting the stage for the great oxidation event billions of years later. Others formed symbiotic relationships, combining metabolic pathways in ways that would eventually lead to the complex, multicellular life we see today. The origin of the first cell was a moment of extraordinary significance. It represented the emergence of life from lifeless matter, a bridge between the physical and the biological, the start of a continuous chain of living systems that would eventually produce plants, animals, and humans. The oceans, once a silent chemical laboratory, became the cradle of life, a testament to the universe's astonishing ability to transform energy and matter into consciousness and complexity. In this way, Earth became more than a habitable planet. It became a living world, an intricate system of chemical and biological interactions, setting the stage for the appearance of the first humans and, ultimately, the civilizations that would gaze at the stars and wonder at the cosmic story of their origins. Millions of years after life had begun, Evolution had already shaped a vast array of organisms, from single-celled microbes to complex multicellular life. Among these primates evolved in Africa, gradually adapting to changing climates and landscapes. Roughly 6 to 7 million years ago, a lineage began to diverge that would ultimately lead to modern humans, a journey of survival, adaptation, and extraordinary transformation. The first humans were not instantly recognizably like us. They belonged to the genus Homo, a branch of hominins that demonstrated significant cognitive and physical advancements over their predecessors. Homo habilis, often considered one of the earliest true humans, emerged around 2.4 million years ago. They were already capable of using tools, a remarkable leap in intelligence and manual dexterity that set the stage for all human innovation. Over hundreds of thousands of years, human ancestors evolved larger brains, upright posture, and increasingly sophisticated behaviors. Homo erectus, appearing nearly 1.9 million years ago, mastered fire, crafted more complex tools, and migrated beyond Africa, colonizing Asia and Europe. The first humans were adventurers, thinkers, and survivors, constantly observing their environment, learning from it, and passing knowledge across generations. The first anatomically modern humans, Homo sapiens, appeared roughly 300,000 years ago. Their skulls, with high foreheads and rounded brain cases, reflected a remarkable expansion of cognitive capacity. These humans created art, developed language, and formed social groups with intricate cooperation. They hunted in organized parties, shared knowledge of edible plants and dangerous animals, and slowly shaped their surroundings in ways that reflected intelligence and foresight. Fossil evidence and genetic studies suggest that these early humans were highly adaptable. They survived ice ages, volcanic eruptions, and migrations across continents. The first humans were not singular individuals, but representatives of small, interconnected communities whose survival depended on communication, collaboration, and ingenuity. They left traces in caves, tools, and even early symbolic markings, indicating that the seeds of culture and consciousness were already being sown. In essence, the first human was not a solitary figure, but the culmination of millions of years of evolution, a being capable of thought, emotion, and creativity. They were the bridge between the ancient biological world and the civilizations that would rise tens of thousands of years later. By walking upright, thinking critically, and shaping their environment, the first humans began a journey that would eventually lead to agriculture, cities, technology, and the modern world. This moment, when humans first emerged with the capacity for awareness, culture, and survival, was a turning point in Earth's story. The planet that had nurtured single-celled life and complex organisms now bore creatures capable of pondering the universe, crafting tools, and shaping their destiny. The first humans were small in number, fragile, and vulnerable, yet they carried within them the potential to transform the world. From the first sparks of human intelligence to the sprawling civilizations of today, the journey of humanity is a tale of ingenuity, struggle, and relentless curiosity. After emerging in Africa, humans spread across the globe, adapting to deserts, forests, mountains, and icy tundras. Early humans lived as hunters and gatherers, forming small groups bound by cooperation, survival skills, and shared knowledge. These small communities laid the foundation for social structures, communication, and the passing of wisdom across generations. Roughly 12,000 years ago, a monumental shift occurred. Agriculture. Humans learned to cultivate plants and domesticate animals, transforming nomadic life into settled societies. This agricultural revolution allowed populations to grow, giving rise to villages and towns, where specialization of labor became possible. Pottery, weaving, and tools evolved, reflecting the increasing complexity of daily life. Humans began to build structures that lasted generations and developed systems to manage food, water, and trade. As cities emerged, governance and law became necessary to maintain order. Early civilizations in Mesopotamia, Egypt, the Indus Valley, and China developed writing systems, codified laws, and complex social hierarchies. Temples, palaces, and marketplaces became hubs of human activity. Knowledge was recorded, mathematics and astronomy advanced, and technology progressed incrementally from bronze tools to iron weapons, shaping societies and their interactions. The story of modern humans is also one of discovery and innovation. Maritime exploration opened vast new continents, creating global networks of trade and cultural exchange. Scientific inquiry challenged old beliefs, unlocking principles of physics, chemistry, and biology that transformed understanding of the universe. The Industrial Revolution mechanized production, urbanized populations, and introduced technologies that altered the very fabric of daily life. Humanity had become a planet-shaping force, capable of harnessing energy, modifying landscapes, and influencing the climate. Social structures evolved alongside technology. Education, art, philosophy, and religion became tools to understand and interpret existence. Political systems evolved from monarchies and empires to democracies, republics, and complex networks of governance. The modern world is a mosaic of human achievement, built upon millennia of trial, error, and ingenuity. From simple stone tools to digital technology, from local communities to global civilizations, humans have reshaped their environment to suit their needs and ambitions. Yet, the building of the modern world is not just about structures and inventions. It is about ideas and culture, the shared consciousness of billions of humans. Literature, music, and art reflect creativity, while philosophy and science reflect curiosity and critical thought. Collaboration, trade, and diplomacy have connected societies, while conflict and conquest have tested resilience. Humanity's story is a continuous unfolding, shaped by our capacity to imagine, create, and transform the earth. In tracing the arc from the first humans to the modern era, we see a profound narrative. Life that began as a single cell evolved into beings capable of abstract thought, engineering, and global impact. The modern world, with its cities, technology, and culture, is a culmination of billions of years of cosmic and biological history, from the quantum void to the first breath of life, from the birth of stars and galaxies to the rise of intelligent humans who could comprehend and reshape the universe. Humans have built a world both fragile and magnificent, a testament to the potential unleashed by evolution, innovation, and imagination. The story of the modern world is not finished. It is ongoing, a living chronicle in which each generation contributes to the unfolding tapestry of civilization. And in understanding this story, we connect ourselves not only to each other, but to the universe itself, the same universe whose first moment set all things into motion, and whose distant stars continue to shine as reminders of our origins.